Thank you for the second introduction. And thanks a lot for the invitation. It's a pleasure and a great honor to be speaking here. I am at Princeton University at the invitation of Sophie Morel, so I would like to thank her as well. I should say I believe that the ability to accept this kind of invitation should not, in my opinion, depend on countries of origin or supposed religion. So the title of my talk is Congruences between Motives and Congruences between Values of Alpha Function. And I will start with a few words about congruences between motives. So suppose M1 and M2 are motives, say, over Q, which are congruent modulo P, the prime. And by that, I mean that for almost all L, the characteristic polynomial of the Frobenius morphism at L acting on the p-adic étale realization of M1 is congruent to the characteristic polynomial of the Frobenius morphism at L acting on the p-adic étale realization of M2 modulo P. And so let me point out that there are tons of examples of this situation. The simplest one maybe is if you take M1 to be one motive M, and then you take M2 to be this motive twisted by a suitable character of P power order, say. And that's typically what is studied in the classical Iwasawa theory. And the results of this talk will apply in this situation, but they are typically very easy in this situation. So this is not my main topic of interest. So let's give other examples. So for instance, take P equal 5, and now look at the two following elliptic curves. So the first one is given by the equation y squared is x cubed plus x minus 10. And the second is given by the equation y squared is equal to x cubed minus 584x plus 5,444. And if you look at the residual representation for P equal 5, they are isomorphic, or they satisfy this condition. In fact, both elliptic curves have good ordinary reduction at P equal to 5. So for those who know this language, they are correspond to points in suitable Hida families. But let me give another example. Now P is equal to 3. And I'm going to look at still two further elliptic curves, E3, given by the equation y squared is x cubed minus 7x minus 6. And E4, given by y squared equals x cubed minus 31,307x minus 1,717,706. And for good measure, I will add F, a modular form of weight 4 and level gamma 0 200. And the motives attached to these three objects are congruent in the sense about for P is equals to 3. And these are not ordinary at P equal to 3. And for those who know this language, they also do not belong to a same Coleman family. Because if you compute A3 of E3 is equal to A3 of E4 is equal to 0, but A3 of F is not equal to 0. But they are still congruent in the sense of the definition. So now, in that situation, there is the question I want to study is what I like to call Mazur's question. Which is in rough form, what about then the special values of the L function? So is it the case that the special value of L of M1 at 0 is congruent to the value of M2 at 0 modulo P.
That's your normalization with zero.
Hmm?
Just trying to see your normalization, the point zero.
Yeah, I chose 0, but I mean, so for these motifs, for this elliptic curve, that would correspond to 1, in fact. But you can take any integer if you want. And in this formulation, this statement is maybe quite meaningless because these are complex numbers, presumably transcendental. But thankfully, with the Burson-Sutton-Dyer conjecture, or more generally, Dolin's conjecture, Beilinsen's conjecture, we can define canonical periods. Finally, maybe by the conjecture of Bloch and Kato. And now these are rational numbers. So the question is less meaningless now. But it is obviously, the answer to that question is obviously no. Because as you very well know, suppose I take the motif Q minus 1, so then its special value at 0 is zeta minus 1. You don't have to divide by any period, because as you all know, this is equal to minus 1 over 12. And this is obviously congruent to 2 modulo 25. But now if you take the motif Q of minus 21, and you compute the same value, so that's minus 77,683 over 276, and that's less obviously congruent to 17 modulo 25. And so in particular, these two values are not congruent. Why not? Because what does hold, thanks to Kummer's congruence, is that there is a congruence if you multiply by the appropriate Euler factor. So in that case, it's 1 minus 5 on one side and 1 minus 5 to the power 21 on the other side. And then these are congruent. And so in general, we should remove another factor at P. And now the question is meaningful and has a chance of being true. So of course, according to the conjectures of Bloch and Kato, these periods are defined only up to a p-adic unit. So maybe it's hard to actually look at congruences. But at least we could ask maybe whether the p-adic valuation of such objects, and maybe even twisted by suitable characters, are related. So say 1 is a p-adic unit, then is it the case that necessarily the other is? With the Euler factor at P removed, of course. And sometimes we can package all these characters in all together, because sometimes motifs have p-adical function. So this is the case for the elliptic curves on this board, for instance. And in that case, you could ask, is it the case that the p-adical function of 1 is a unit in the relevant Iwasawa algebra if and only if the p-adical function of the other is a unit. And here, lambda is a completed group algebra, or maybe gamma is the Galois group, the cyclotomic extension, ZP cyclotomic extension. More generally, A, ZP, or ZP power G extension. So why do I call this question Mazur's question? It's because the earliest absolutely explicit formulation of it I know is in a paper by Mazur from 1979. And there he asked the following question. I paraphrase, but only slightly. Is the algebraic part, and he puts it between scare quotes, of the L function of an eigencusp form twisted by a Dirichlet character evaluated at some integer, modulo A, and that is a prime ideal of the Hecke algebra. So is this value given by a formula, and that's also in scare quotes, depending on the Jacobian of the modular curve at n, of level n, and you take the A part, and of course, you look at this object with its Galois action. So is this value modulo A able to be described solely in terms of that object? And in this paper, I'm going to mention a few historical facts about this question. So first of all, in that very paper, Maser gives a positive answer if A is Eisenstein. So if the cusp form F is congruent to an Eisenstein series, then he shows that modulo the maximal ideal, this Eisenstein maximal ideals, the L function of F can be expressed in terms of two Kubota-Leopold p-adic L function, one corresponding to each of the characters of the Eisenstein series. So there he has his formula depending on the Kubota-Leopold p-adic L function. Maybe I should say, why did he put algebraic parts in scare quotes? At the time, the Bloch and Kato conjecture is not even formulated for modular forms. So we don't even have a conjecture for this special value at the time. So that's why he put it. Two, almost 20 years afterwards, Batzal showed that the answer is yes if you have two eigencusp forms, F1 and F2, and they are congruent modulo P, and they are both of weight 2 and nu of level n for some n. So if you have two forms, both of weight 2, both nu of level n, and they are congruent, then their special values are congruent in the sense of this question or in the sense of Maser's question.
Again, S is an integer with some parity. What is S?
What is S? Okay, of course. So here, because you are in weight 2, you would have to take S equals 1. Yeah, the critical points. But you can twist by any character. But lest we are too optimistic, let me mention 3, that if you take the p-adic L function of the elliptic curve E1 at p equal to 5, and you compute it, then you can see easily that this is a unit in lambda. Whereas the p-adic L function of E2 if you write it down in Weierstrass preparation theorem form, there is a distinguished polynomial of degree 5 and then a unit. But anyway, it's not a unit in lambda, even though E1 and E2 are congruent. And likewise, if you look at the two over elliptic curves and the modular form that were congruent modulo 3, then you can check that for all character chi of p power order, the p-adic valuation of E3 twisted by chi at 1 is equal to the p-adic valuation of the modular form F at 1, and that is actually 0. But the periodic valuation of the special value Euler factor at P removed of E4 twisted by any character, P power order, that is always strictly positive. So the most naive answer that we could give to Mazur's question would be wrong. If there is such a formula, this formula, so Mazur was wise to put scare quotes around formula because the most naive type of formula cannot work. So the question becomes, could we have predicted this and can we explain this? And the answer is yes. At least in the ordinary case. So in our examples, that's for E1 and E2 and P equal to 5. And we can do this with the following proposition, which is due to Emerton, Pollack, and Weston, 2006. So I'm going to apply the proposition to that specific case. So for that, I need to introduce a set sigma. It's a finite set of primes, and actually it's the set of primes 2, 7, and 13. And I will call R sigma the reduced, nearly ordinary periodic Hecke algebra acting on forms of level at most 364. And let me remind you that this is 2 square times 13, which are the 52 weeks of the year. And these are the 364 days of the year. OK, so let me tell you that the dimension of this ring, the cruel dimension of this ring, is 3. And I'm going to draw the spectrum of its ring with P inverted. So because P is inverted, now I'm in dimension 2, relative dimension 2 if you want. But one of these dimensions is accounted for by the cyclotomic deformation. So if you have a point, say x1, then there is a cyclotomic deformation, which I will represent by a vertical line, and that's one dimension. So now there's just one dimension more, and in that case, the spectrum of this ring with P inverted is the union of two irreducible components. Which cross at some point of characteristic 0, and both of which are smooth. And the points x1 and x2 correspond to the two elliptic curves E1 and E2. So what did Emerton, Pollack, and Weston prove? They proved that in this situation, there exists first an object L sigma, which is an element of R sigma. And for I equal to 1 and 2, an object Li, which belongs to R sigma over Ai. And these are the minimal prime ideals. So this is A2 and this is A1. The irreducible components correspond to minimal prime ideals A1 and A2. Such that, first of all, if you specialize at xi the elements Li, you get the periodical function of the elliptic curve Ei. So x1 of L1 is the periodical function of E1, and same for E2. And also, if you take L sigma and you take it modulo the prime ideal Ai, then you get the element Li times a product of Euler factors for the primes in sigma. So in what sense does this statement explain this phenomenon? Well, if you believe that this is a unit, then because x1 of L1 is the periodical function of E1, it has to be that L1 is a unit. However, if you compute the Euler factor at 7 of A1, so these terms from I equals to 1 and L equals to 7, then this is not a unit. And how do I know this? Because I can specialize it at x1 and compute it for E1. That's just the Euler factor for the elliptic curve. But this means that L sigma is not a unit. Because L sigma modulo A1 is a non-unit. And so L2 times the product of Euler factors, but now for A2, this cannot be a unit. But again, if you compute all these Euler factors, they are all units. And so it has to be that L2 is not a unit. However, for all L in sigma, the Euler factor at L of A2 is a unit in R sigma over A2. And so L2 is not a unit. And of course, the periodical function at E2 being the specialization of L2 is not a unit. And with a little more effort, we can even predict what we observed, I think, hopefully here, that is that there is a polynomial of degree 5 appearing. But at least this argument shows that LP of E2 cannot be a unit. So that's Emerton-Pollack-Weston result. And I am going to be interested in an algebraic variant of this result in this talk. So why is that? Well, first, if you look at the proof of Emerton-Pollack-Weston of this proposition, it's not so easy. And more specifically, it relies crucially on the Q expansion principle and on Hiara's lemma. And that's two ingredients that are notoriously hard or missing in other situations. So the hope is that if I can give a proof, a purely algebraic proof of this result, then it could generalize. In fact, I don't think that an analytic proof of this result exists already for modular forms which are not ordinary. What do I call by an algebraic variant? Well, now, thanks to the Bloch-Kato conjecture, we know, or at least we believe, that if M is a motive, there exists a so-called zeta isomorphism from something called a fundamental line. And that, by definition, is the following object. It's the determinant over O of the étale cohomology complex of Z with P inverted, with coefficients in some T. tensor with the determinant of T and invariant part under conjugation, but first twisted by -1. So that's a morphism from this object, an isomorphism from this object to O. And I should tell you what T is. Yep.
Could you remind us what condition you have on P in the prime P?
Here.
Yeah.
So here you need all your motives, or modular forms in that case, to be P ordinary. Okay. So if you're, and of course for the theorem to be true, you might need rho bar to be absolutely irreducible and P distinguished, but yes. But the important condition is that you are P ordinary. Okay.
P be equal to 7.
Can P be equal? Oh, I mean, for these motives to be congruent, you need to have P equal to 5. If you want to apply this theorem in, in that situation. But of course, there is a general theorem. And I mean, is your question that can P be into sigma in general?
Yeah.
Yeah, and the answer is yes. Yeah. So what is T here? T is any lattice in the p-adic eta regularization of M, which is GQ stable. And by Tate's formula, this object does not depend on the choice of T. So now, if you are not familiar with Bloch-Kato conjectures, Bloch and Kato conjectures, this merits some elaboration. So you should think of this morphism as a formula predicting special values. So in particular, if the conjecture is false, this object has nothing to do with special values of L function. But if you believe that the conjecture is true, then this can be understood as a formula predicting special values. And so the conjecture I'm going to state can be understood in this way as interpolation of the values predicted by the conjecture, which might or might not be the real values, but these are the ones we predict. So this is the conjecture, the algebraic generalization of Emerton-Pollack-Weston. So you can compare with this side. So suppose you are given a Galois representation unramified outside a finite set sigma with coefficient in some reduced ring R sigma. Then we might conjecture with Kato that there exists first a fundamental line delta sigma, and for all minimal prime ideal of R sigma, a fundamental line delta A. Zeta isomorphisms from delta sigma to R sigma, and from delta A to RA, which is R sigma over A. So you should think of this as formulas predicting special values, but over the whole family. Or if you want, interpolation of formulas. 2. Well, I said here that I could compute that the Euler factor was or was not a unit simply by specializing it at the elliptic curve. So I need to be able to do that. So for all A and for all L, maybe different from P, I need some Euler factor A such that if I specialize at a point X, and if this point is attached to a motive, then I can compute the Euler factor of its motive, and I want them to be the same if X is motivic. And finally, of course, I want a relation like this one. So meaning again, if X is motivic, if I compose a specialization with the isomorphism zeta A, I should get the isomorphism zeta of Mx, this one. So to keep comparable notations, I will make explicit the coefficients. And if I reduce zeta sigma modulo A, then that should be zeta A times the product of the Euler factors at A. Exactly as in the case of Emerton-Pollack-Weston. So again, if you want to think of these isomorphisms as formula predicting special values, then this statement is an interpolation because it tells you take the formula over the whole irreducible component, specialize it at some motivic point, you get the formula corresponding to a given point. And that once tells you that you can interpolate the formula over the whole ring if you take care of Euler factors at sigma. But now if you actually read Cato, you will see that he puts condition 4. And condition 4 is same as 3, but for all x, say from R sigma to QP bar. So not only those attached to a motive, but any point. So I'm going to put a question mark here. So that's something that he wants, and he has reasons to want it, but we'll discuss it later. So now we'll state my main result. So if you look at a conjecture again, its input is a Galois representation unramified outside the Southern set sigma. And so I'm going to assume that this Galois representation occurs in the completed cohomology of tower of Shimura varieties. And if you have tower of Shimura varieties, you have Shimura variety to begin with. So you have an underlying reductive group G. So here G is either A, the unit group.
So tower means congruent subgroups with some prime.
So this is what it means, but I'm going to explain precisely what occurs in the completed cohomology mean. But that's what it means, yes. So G is either the unit group of quaternion algebra. So B over F is a quaternion algebra which is split at most one infinity place. So at 0 or 1 infinite place. And F is totally real. So note that GL2 over Q is OK. Another case, so the reductive group G could also be a unitary group compact at infinity. Or C, GSP4 over Q. And that's not quite all the hypotheses. So this rho sigma, it should occur in such a completed cohomology. And this completed cohomology should be localized at a strongly non-Eisenstein maximal ideal. And I will explain this as well. But before explaining precisely the hypothesis, let me point out, oh, so these are the hypotheses. So what is the conclusion? Sorry. Then 1, 2, and 3 hold of the conjecture. 1, 2, and 3 hold of the this holds of conjecture. Yeah. But 4 doesn't in general. In an interesting way.
In the first, these unitary groups can be any dimension?
Yes.
B.
Yes. No, in the case B, yes. Yes.
I mean, in your example, the thing was 3-dimensional.
Yeah. So in example B, you can have a very, very large dimensional ring. Yes, very large family. But already in the quaternion algebra, if you take f of large degree, it can also be large. Yeah, there are families of very large degree here. Yes, so before explaining the meaning of occurring in completed cohomology and strongly non-Eisenstein, I would like to give an example. Just like the proposition of Emerton-Pollack-Weston allowed us to analyze the case of E1 and E2, I would like to analyze briefly the case of the two elliptic curves and the modular form that I introduced in the beginning of the talk. They were called E3, E4, and F. So in that case, these elliptic curves and this modular form, they occur as the classical points in a ring in the Hecke algebra R sigma, which is of dimension 4 now. So again, I'm going to draw its spectrum with P inverted, so that will take care of one dimension. And again, I will neglect the cyclotomic direction, so that will take care of another one dimension. So I will attempt to draw surfaces. Yeah. So what do we get in that case? So we get an irreducible component like this, and this one has a point which is E3. And yeah, and another, I don't know, another irreducible component like this, which has E4 as a point somewhere, and there's a third component and this one has F on it. And I do know for sure that they are on different irreducible components. And I do know for sure that this one meets that one and this one meets that one, but I don't know if these two meet. That I don't know.
What example do you think?
This is E3, E4, and F. So these are two elliptic curves. And maybe I will mention that E3 is of level 40. And E4 is of level 1640, and F is of level 280. And in that case, the special values of E3 are p-adic units. special values of f are p-adic units, and the special values of E4 are not p-adic units. And I want to, so that you could check computationally, but I want to see if my algebraic variant of Emerton-Pollack-Weston can predict this. And we are not in the ordinary case, so we cannot apply their proposition. So what I'm going to look at is two finite set of primes, and one is 2, 5, and 7, and the other is 2, 5, and 41. And it's easy to check that the zeta isomorphism corresponding to the component A3, the one which contains E3, that, if you unravel the formula, yields p-adic unit. But what happens then is that all Euler factors, so for all L in sigma 2, no, in sigma 1, the Euler factor of AI is a unit. And here I is equal to 3 or 5, I guess. So that would be A5. And so zeta sigma 1 yields units, p-adic units. And same for zeta A5. But on the other hand, on the irreducible component number 4, so the one containing E4, we have that the Euler factor at 7, at 41, of A3 is not a unit. Whereas the Euler factor at 41 of the component A4 is a unit. And so by the same reasoning as before, when we discussed the case treated by the proposition of Emerton, Pollack, and Weston, you deduce that the p-adic L function, or the special values of the L function at this point, have to be non-units. And again, how do I know that these are units or non-units? Using proposition 2, I can just specialize at the motivic point and compute there. So that's the use, one potential use of this theorem. So now let me state in more details the hypotheses of the theorem. Let me explain them, let's say.
You can deal with compact unitary groups where there are no Eisenstein series at all, right? So,
yes.
so that your theorem would relate things which are not Eisenstein.
No. But I mean, all these results relate things that are not Eisenstein. All these elliptic curves and modular forms have irreducible residual real representation. The Eisenstein case for modular forms is basically already treated by Maser. No. So I will say a couple of words on completed cohomology. So for that, I consider Gx a Shimura datum. So G is a reductive group. And given this datum, if I have a compact open subgroup U of the finite adelic points of G, then I can attach the Shimura variety YU. And for me, it's OK if the dimension D is 0. I will still call this a Shimura variety. And I'll be particularly interested in the use of the form UP and U outside P, with UP a compact open subgroup of the p-adic points of G, and UP, U outside P. A compact open subgroup of the finite adelic points outside P of G. So now if I have such a group U, I can consider YU. I take its complex points, and I look at cohomology in middle degree with torsion coefficients. And so this is UP, U outside P. And then I take the direct limit on the group at P of this, and then the inverse limit on S. And that, by definition, is the completed cohomology of degree D of tame level UP and with coefficients ZP. So this direct limit is just a union, so taking many groups, many cohomology groups. So on this cohomology, there is an action of the Hecke algebra. So also here, so I can localize at some maximal ideal the Hecke algebra, and then I get an action of a local Hecke algebra. And if I choose a suitable Hecke algebra, it can be, I can easily make this reduced. So now I should explain what it means for M to be strongly non-Eisenstein. So M is strongly non-Eisenstein if A, the completed cohomology vanishes after localization at M if I is not the middle degree, and B, the residual representation attached to M is absolutely reducible. I believe that, in fact, Matthew Emerton has conjectured that B implies A. So B is what is usually called non-Eisenstein. And so A is strongly. And so there is a conjecture that B implies A, and certainly this conjecture is true in case A and B of the theorem. So case A was a quaternion algebra, and case B is a unitary group compact at infinity. But in case C, I don't think it is known. At least I don't know it. So I will put this condition. I think that is so I think it's that is it or closely related to it, but I don't know enough about these questions of growth to answer definitely.
And why only GSP4? What's special about it?
Just because it has cohomology in many more potential degrees. Yeah. So in that case, middle degree is H3, right? And I don't know that H1 vanishes after localization at such under condition B.
Maybe provable from the trace form.
I don't know. Maybe some people do know.
If it's related to the growth rate.
So now a proposition definition. So you can take it as the definition of occurring in completed cohomology. And that is, under this hypothesis, there exists a Galois representation and ramified outside sigma with coefficients in the reduced Hecker algebra with a Zariski dense subset of classical points or motivic points, so I'm going to call it spec mot, such that if X belongs to this set of motivic points, then 1, the Galois representation rho localized at X is adapted to some cohomological automorphic representation of the finite idyllic points of G, adapted in the sense of having common L factors. And 2, if I restrict rho X at GQL, the local Galois group for L different from P, then this is pure in the sense of the weight monodromy conjecture. And I should say that this proposition is not due to me and probably well known to experts, but after the hard work is in proving that condition 2 holds. And this has been done by many people depending on the different group we might consider. But then even when 2 is known, the statement that there is a Zariski dense subset of points is not completely formal. And for experts, I will point out that it relies on the degeneracy of Emerton's spectral sequence relating Lie algebra cohomology and automorphic representations in completed cohomology. So this is not a completely formal statement, but presumably well known. And you can take this as a definition of occurring in completed cohomology of Shimoda varieties. So now, I can give a very quick sketch of the proof of the theorem. So recall that we needed first a fundamental line delta sigma. Well, Cato suggested a definition. And that's the determinant of the étale cohomology complex with coefficients into sigma times the determinant of the Galois representation itself with some normalization. So inertia invariant. And we also needed something for any irreducible, any minimal prime. And again, Cato suggested a definition. So here it's important that sigma is inverted. And precisely here, only P is inverted. But apart from that, it's the same thing. But I put a question mark here because there is a problem. And the problem is that the second object is not well defined. And why is that? Well, for experts, I will recall that the determinant functor makes sense only for perfect complexes. And this is not known to be a perfect complex, whereas this is a perfect complex. So this makes sense, but this might not. But let's forget it for the moment. If we take these definitions and just assume that it works, then at least there is something good that happens, is that by construction, this definition will satisfy that Z sigma mod A is equal to ZA times the product of the Euler factor at A. And as for the composition of zeta A with a specialization x, that will be the specialization at x times the product over L of the quotient of the image of the Euler factor through x divided by the Euler factor at x. But if you recall the statement, so that's very formal. If you take this definition, you apply x, you get this. But if you recall the conjecture, we want that x composed with zeta A is zeta x. So we want this to be 1. So it is enough to solve the first problem and to show that the image of the Euler factor is equal to the Euler factor at the image. And that I will call star star. But here is some bad news now. And that this fails. So this is not true. Which might not be so surprising because we have not used any hypothesis on x. But that would be statement 4 of Cato. So statement 4 does not work. And the reason is, if you go back to the very first picture I drew, is that it fails at this point. But at least with these definitions, it holds if x belongs to the motivic subset of points. And so that is enough for the conjecture for 1, 2, 3. Provided, of course, we can solve star 1, but that I'm not going to talk about. In conclusion, I would like to explore the following question. Can we do something about 4? So is it possible to salvage the conjecture even where it fails? And the answer is yes. In a natural way, I believe. Because if you look at the problem at this point, the problem at this point is that this part of the fundamental line does not behave as we want it to behave. But this one does. So that is not OK, and that is OK. So what we're going to do is change the definition. And we're going to change that one. So that one becomes not OK, but in a way that we compensate this one. And because now my time is up, I will just give the answer to how to do this. This object is something like the determinant of the Betti cohomology realization of the motive. So in a p-adic situation, it should be the determinant of the completed cohomology. But the completed cohomology is huge, so that's way too large to take the determinant. However, the completed cohomology contains some automorphic representation and these objects are very large, but they have some sort of determinant. which is called the Bernstein derivative. So the solution is to replace the nonsensical determinant of completed cohomology by top Bernstein derivative by the top Bernstein derivative of this object. And in order for this to check that this makes sense, you need the result of Emerton and Helm and David Helm on the p-adic interpolation of the local Langlands correspondence. And then for that definition, you recover this property even at this point x. Because now both objects do not commute with specialization, but they do not commute with specialization in a way that compensates exactly. And so we recover the theorem. And now I stop.